Before moving on to our first example of a dynamic program that solves a real problem, we're going to introduce the idea of a directed acyclic graph, or DAG. We're doing this for two reasons. First, when we describe our first problem, it has to be described on top of a DAG. That's part of the input. But secondly, a DAG is very much like a computational tree for a dynamic program. We'll see this evolve in our first example. So a DAG is a graph that's directed. It's a graph that has a set of nodes and a set of arcs. And importantly, there's no cycles. A cycle is any set of arcs so that we can return or find a path from a node back to itself. In this case, in this cycle, if we start at this node, we can go around the graph and find a path that goes back to the node, and hence there's a cycle. In a DAG, or directed acyclic graph, there are no such cycles. Directed acyclic graphs can get quite large and quite complicated. There's algorithms to test whether a particular graph is a directed acyclic graph, and we can find these packages in any sort of typical programming language. We're not going to go through algorithms to identify DAGs. The only algorithm that we're interested with respect to DAGs is the topological sorting algorithm. In this case, we can consider the topological sort as an input-output sort of problem. Our input is a directed graph that happens to be a DAG. The output is an ordering of the nodes, and we'll call this ordering O. The key property of this ordering is that if we have any arc in our arc set A, the first node of this arc has to have a lower index than the second node of this arc. This is the index with respect to the ordering. It's helpful to see the topological sort from a very visual perspective. Here we have a particular graph, G equal to VA. And on the nodes, we have the labels given to it by the topological sort. So our labels O are in blue. We can see the labels on this graph, but it's more interesting if we put these labels in a linear ordering, like we did here. This is the same graph. It has the same set of nodes and the same set of arcs. The difference now is that we've taken our first node and we've placed it at the beginning of this line. We've taken our second node and placed it at the second node of this line. You can see that every edge in our graph is accounted for in this linear ordering. For example, this arc between 1 and 4 is present here. We can do this for all the arcs. When we represent the topological sort in this visual way, it's easy to see what a topological sort is. We'd like to organize the nodes in a linear way so that all the arcs point in one particular direction. We're going to use the topological sort pretty frequently in dynamic programs, and specifically in the next problem we're going to introduce. And we're going to use it by saying, given a DAG, we're going to take the topological sort of it. The topological sort is actually the ordering O.